Welcome to our latest Full Steam Ahead webinar. Thank you so much for joining us. If we haven't met yet, I'm Anina Peterson. I'm the Director of Science and Research here at Geothermal Rising, and I'm delighted to be moderating this webinar for you today. As you know, we have some amazing speakers on EGS, John McLennan, Colleen Barton, and Kareem El-Sadi. But before we hear their presentations, I have just a few announcements. I want to let you know that we are recording this event and it will be available on our YouTube channel in the next few working days. Also, we ask that you use the Q&A function at the bottom of your Zoom screen. You can enter any questions you have at any time throughout the webinar, and we will answer those questions in the Q&A section after all three of our presentations have wrapped up. We also want to take a moment to thank our members for your continued support. Your membership helps us to continue our mission at GR to build and strengthen the geothermal industry, and we really appreciate it. So we'd like to thank our Earth Energy visionaries. They are Baker Hughes, Calpine, Ever, Exceed Geoenergy, Quays, SLB, Turboden, and EggGeo. A big thank you to our geothermal champions, BHE Renewables, Chevron, Fervo, Burns & McDonnell, COSO Operating Company, XPro, Neighbors, NOV, Ormat, Curita, Oxy, Sinclair, Southern Company, and Halliburton. And last but not least, a big thank you to our clean energy enthusiasts, Central Washington University, DTEC Rotary Steerable, Geologica, NREL, Valoric New Energies, Imperial County of California, Zanskar, Baseload Capital, XGS Energy, and Amoresco. We also want to let you know that we hope to see you back here in a couple of weeks for our next webinar. It will be held on September 5th, and it will be the first of a series of spotlights on our national labs. So we'll be hearing about the awesome geothermal research going on at Pacific Northwest National Lab. So as a reminder, you can find a link to register and recordings of our previous webcasts on our website. Finally, we hope to see many of you in person at some of our upcoming events. We will be at Image next week here in Houston, where we have organized the Geothermal Hub. It will be up on the 3rd floor, so hope to see many of you there. And then looking ahead to October, which is just around the corner, as you all know, we have a lot of activity going on, including our annual conference, October 26th through 29th in Reno. But ahead of that, we are having our 2nd annual Indigenous Geothermal Symposium, as well as a brand new Geothermal Discovery Day. So hope to see you all at the end of October in Reno. Looking ahead to 2026, we have 2 events happening in Houston, April 7th and 8th. They will be the Geothermal Investment Forum and then a Geothermal and Oil and Gas Mutual Challenges and Opportunities, which will be a very technical symposium. And then we have our annual Capitol Hill Day that will be April 28th and 30th this year in Washington, D.C. So without further ado, I would like to introduce our first speaker, John McLennan. John McLennan is a professor of chemical engineering at the University of Utah and co-PI of the Utah Forge project that we all know and love, and we'll get to learn more about here shortly. Before joining the university in 2008, he has nearly 30 years of experience with oilfield service and consulting companies. So, John, I will pass it over to you.
Hello, everyone, and thank you, Anina. Today, I would like to briefly talk about Utah Forge. And as you know, Forge stands for Frontier Observatory for Research in Geothermal Energy. And today, we will talk about the status of Forge. We will talk about the successes, and we'll bare our soul and talk about some of the challenges that we see coming up for the near future at Forge. So a 30,000 foot view of Forge is that it is a facility that's designed to de-risk EGS technologies. And to do that over the last almost a decade, we have 10 wells in place at a facility in west central Utah. 3 of these are shallow permanent seismic monitoring wells, and those are supplemented by a surface monitoring, microseismic monitoring network. There is 1 shallow water well that supplies water for operations. And there are 4 deep vertical monitoring wells in which geophone chains are run while we're monitoring fracking activities and circulation activities. And then there are 2 highly deviated wells. They're deviated 65 degrees, intentionally at 65 degrees, so that logging tools can be run on gravity. In these 2 highly deviated wells, we have run 2 stimulation campaigns to interconnect those wells hydraulically with hydraulic fractures. So to get a perspective of this, you can see that the white arrows indicate the groundwater and monitoring wells, and the blue line indicates an injection well that was drilled at 65 degrees in the direction of the minimum principal stress, fracked in 10 stages over a couple of years. And above that, 300 feet immediately above that, is the well that's horizontal projection, or its projection to the surface is shown with the red dots. And that well, known as 16B, is the production well. And the production well has also been fractured. So if we look back and look at some of the highlights of Forge, one of the things that has turned out particularly well is to be a participant in a transformative change in geothermal drilling, moving from roller cone bits, shown here, to polycrystalline diamond compact bits, where we've had tremendous success with these bits. So, and that's illustrated in this particular drawing. So you can see the y-axis is the measured depth. The x-axis is the on-bottom hours. That's how much time you're actually drilling. And you can see that the first well that we drilled was 5832, and that well was actually drilled with roller cone bits. And so to go to 7,500 feet with roller cone bits, we were proceeding at maybe 5 to 10 feet per hour. And it took almost 600 hours to get to 7,500 feet. When we drilled our first inclined well, we drilled that well exclusively with polycrystalline diamond compact bits, PDC bits. And you can see that to drill to a greater depth took about half the time. And progressively, this has improved with time, as you can see for the wells. And ultimately, the 16B is our production well. Now, I have to say that Fervo, as you'll hear, has taken this even further, where they've really, really refined the drilling process. And this makes a huge difference in the CapEx of geothermal operations. So to recap drilling, I mean, I think Forge has demonstrated the viability of PDC bits. One of the things that was successful at Forge, in addition to that, was the interactive near real-time bit redesign that was facilitated by a superb degree of cooperation with bit manufacturers. And certainly in the first well, that was with NOV, Reed Heikelhoff. We've subsequently had very good relationships in our drilling with the other drilling bit companies. So what we've seen is dramatic increases in ROP, and also substantial increases in time on bottom are recorded. As I said, you'll hear more about this, I'm sure, from subsequent speakers. We've also embodied the philosophy that Forge is a facility for testing third-party products, and we've tried out rotary steerable technologies. We've tried out particle drilling. We were lucky enough to try out Ever's insulated drill pipe, which was very successful. However, these are some of the successes. There are some things that we need to think about, particularly as we move away from sort of an almost ideal drilling environment at Forge. In many other parts of the world, geothermal drillers encounter significant interfacial severity, and there tends to be a correlation between bit DBR, complete bit failure, with interfacial severity, which is usually associated with natural fractures where there's a substantial contrast in mechanical properties going into the fracture and out of the fracture and subsequent bit failures. Lost circulation in places outside of forge remains a significant problem in EGS if you're drilling ahead. And these two also interrelate to the ability to have improved characterization in advance of your drilling and understanding how that affects your drilling operations. So drilling has some lessons learned and some lessons to be learned. And it's similar with the hydraulic fracturing campaigns that were undertaken to interconnect the wells at Forge. And in fact, there have been two drilling campaigns, one where 3 stages were pumped at the bottom of the injection well to assess microseismicity and to scale where the next well would be drilled. Subsequent to drilling the second well, an additional 8 stages were pumped in the production well and 4 stages, 8 stages in the injection well and 4 stages in the production well. The stages in the production well were guided by frac hits that were monitored by fiber optics that had been successfully cemented in the production well. So if we want to recap the hydraulic stimulation, here are some of the things we found. First of all, it was a demonstration of successful hydraulic fracturing in a granitic setting. And you can see some microseismicity from our first fracking campaign where three stimulations were done at the toe of the production well. Also, in my mind, we have a clear demonstration of the requirement for proppant in these fractures. That production logging testing after the fact has shown that fracture stages that were not propped did not take fluid. And so this really reinforces the need for proppant. However, what are the buts here? Well, first of all, there's still a lot to be learned about the mechanics of completion. How many clusters are important? What sort of cluster spacing? How we can keep fractures independent and maximize the growth. The second thing that is the obvious one is proppant durability. In these environments, certainly silica sand ultimately is probably not going to work out, and using alternative proppants, it is going to increase the initial costs, but it'll be of value in the long run. The next thing that is relevant are treating fluids. If you're going to have different proppants and you're going to increase the concentration of your proppant, which I believe you have to do to increase the conductivity between these fractures, you're going to have to look at new generation treating fluids that have the viscosity. And then finally, one of the things that was really very interesting with this is that there were fracturing corridors. So what do I mean by fracturing corridors? Well, let's look at this plot. Let's look at the east-west extent of the two wells on the x-axis and the vertical depth on the y-axis. So the bottom line, red line, represents the injection well. The top blue line represents the production well. Each one of those dots is either a set of clusters or an individual frac stage. And what you can see from these frac stages, particularly looking at stage 8, is that these stages are not uniform, they're not regular, and that there are interactions of flow. That if I look to the right, I can see that the first 3 frac stages all converged on the same set of frac hits, determined by fiber optics on the production well. So that's one corridor. Then if I look at stages 8, 9, and 10 to the left, uphole, we can see that the end of stage 8, stage 9, and stage 10 all flow out of the same exit. So really, there's heterogeneity, there's natural fractures, possibly some minor faults that are playing a role and need to be considered. And so once again, this goes back to the whole concept of reservoir characterization. So how do you test all of this out? We've carried out some short-term and intermediate-term circulation tests, pumping down the injection well, producing through the fracture system, and producing out of the production well. And here is an example from a 28-day circulation test, where the red curve is the surface injection pressure, and the blue curve shows that we maintained a constant rate of 10 barrels per minute over a relatively large period of time. So I've got some numbers on here, and I want you to remember what those numbers are pointing to. That number is pointing to a pressure that's about 2,900, almost 3,000 PSI to circulate 10 barrels a minute. The next thing that we want to look at was, well, you pumped in a certain amount of fluid, how much came out? Okay, so the red curve is associated with the secondary axis, and it shows the surface temperature of about 385 degrees Fahrenheit, pretty constant, not going down. Good sign over a month. What'll happen over 2 months, 3 months, 4 months is yet to be seen. And then the efficiency is shown in blue, and that's the ratio of the mass flow rate out divided by the mass flow rate in. And it was approaching 90%. So let's remember that too when we come back for a recap. We have run production logging tests at various times, and we have seen that there's some degree of uniformity, but not all clusters are taking fluid. And so there's still room for optimizing the clusters in the fracturing treatment. And so that's the third thing to remember as we come up to this slide here. So a recap of our circulation, which is really a reflection of the current success of EGS, is that we've had successful circulation with about a 90% mass flow rate ratio efficiency. And that's pretty promising. But what are some of the drawbacks? We've had a successful circulation with a 90% efficiency. 90% seems pretty good. However, if you start to think, where is that 10% of the fluid going? And I'm circulating up to 60,000 barrels a day maybe in a production injection well combination. That's a substantial amount of fluid that's lost. So it's anticipated that this will decrease over time, and as you have a network of wells, that it will go down. But this is going to be a challenge because replacing that water is going to be expensive and could have other consequences. So that was the number 2 point that I pointed out, that 90% efficiency isn't good enough. The next thing is the parasitic loading. We saw that we treated these wells at about 2,900 PSI. If one does the calculations for the hydraulic energy that's required to pump 10 barrels a minute at 3,000 PSI, it's not insignificant. And that parasitic loading goes off your net power. So this is certainly a solvable problem. It relates to either near wellbore restrictions or inadequate conductivity of the fractures. And so this is something that needs to be resolved in the future. The third point is conformance control, where you're looking to get equality of flow through all of your perforations. And this is something that the industry will have to work on to understand how to get conformance and how to mitigate it if you don't have conformance. So finally, to sort of summarize, Forge has been an outstanding success in learning about drilling, stimulation, and EGS in general. And it offers a very, very positive reflection on the future. And so we will continue in our phase 4 at Utah Forge with drilling one additional well, with additional fracturing, with additional circulation. Forge funds R&D programs, and we'll do our best to support commercialization that is done elsewhere. And so with that, I think I've probably used most of my time, and I would like to thank the Department of Energy for funding this particular project.
Thank you so much, John. That was great. Reminder, please submit your questions in the Q&A functionality to answer at the end. Next, I would like to introduce Colleen Barton. Colleen Barton is Principal Advisor, New Energies at Baker Hughes Gaffney Klein Energy Advisory. Dr. Barton holds a PhD in geophysics from Stanford University and has 40 years in the industry. She's co-founded Geomechanics International and is a senior specialist in the area of geomechanics, fracture mechanics, reservoir permeability, and dynamic stimulation applied to geothermal reservoirs. Colleen also holds 5 patents and has over 80 peer-reviewed publications in her discipline. So thank you so much for being here, Colleen, and we will pass the stage over to you. Please go ahead and share your presentation and take it away.
Are you seeing the presentation now?
Looks great. Go ahead.
Great, thanks. Hello, everyone. Nice to be here. What I want to talk to you today is about three-dimensional modeling of enhanced geothermal systems for both heat production and economics. Our team at Baker has developed a phased approach to assessing geothermal potential at a prospective site. We start with a play fairway analysis to sniff out the quality of the resource. Then for the sites that we assess, we develop a 3D geomodel that provides the base static model for all of the dynamic modeling to follow. And at this phase, we design the conceptual well trajectories and the stimulation zones. And then in the pre-feasibility stage, we look at the fracture data, develop a DFN, natural fracture data. And we also design hydraulic stimulations for hydraulic fracturing and hydrosharing. We upscale the hydrofrac and DFN fracture models, transmissivities, to the full permeability tensor. And this provides the base for the reservoir dynamic modeling, where we do the production forecasting and the economic analysis. We down select from that set of sites when we look at the comparison there from the preliminary economic modeling, and then go through the full physics 3D multi-stage stimulation modeling using our HPC to simulate the coupled thermo-hydromechanical behavior of fracture networks, propagating fractures without a pre-existing natural fracture network and within a pre-existing natural fracture network. And then we refine that production, the production forecasting and the economic analysis. So let's take a look. I'll take you through a study we did for a set of clients here in South Texas. We had a robust PFA and down selected 2 sites, one to the south Texas here in the Eagle Ford, and then one up in the Haynesville. So this is just an example of the geomodel build. We obviously use we need a thermal model. So we use some regional data and data from the client that they can provide. But we also need, of course, for the propagation, the fracture propagation modeling, we need rock properties and full geomechanics in 3D, all of these parameters. So in phase 2, as I said, we have the DFN model, and this connected natural fractures, and then we have a hydrofrac model. These are the explicit fractures with no DFN. They're 150 meter half lengths, and they have a variable hydraulic aperture. And then we put that through the reservoir modeling, flow modeling, to look at the thermal output over 30 years. And for these 2 cases, with and without the natural fractures, we look at the sensitivity to injection rate, drawdown, cluster spacing, well spacing, and then we compare the sites for further down selection. This is an example of the transmissivities from one of the examples of the DFN, and then upscale to the permeability tensor, Kx, Ky, Kz in the bottom row here. And these are the results of the phase 2 dynamic simulation, dynamic flow modeling. And for these particular cases, we have 2 wells, they're lateral wells, 300 meters apart. This is the permeability field. The top row is just the natural fractures only. The middle plots are temperature. And you can see here the thermal output put over 30 years with the different scenarios that we've tested. All of them have a less than a 10% decrease over 30 years. The hydrofrac only case, again, this is the permeability, the temperature, and you can see the breakthrough here after 30 years. The hydrofrac only case has a much greater sensitivity. And so we have more decline of 30 to 45% over 30 years. So this is another step in the down selecting for the site screening. And then we go into the final phase where we do the full physics modeling of the hydraulic stimulations with or without pre-existing natural fractures. For this, that's 60-meter long stages. We use slick water, a little over an hour injection time, the 13 stages totaling 800 meters. And we do the dynamic reservoir flow modeling, once again, using these numerical models and looking at the thermal output over 30 years. And again, we're using propagating hydrofracts with and without natural fractures to make a comparison. We also built a zonal isolation model into the reservoir modeling. And I want to say right here that I didn't see John's slides first. So, so this is right to his point. Because we wanted to look at the sensitivity to well separation and to zonal isolation. So this is the results of the multi-stage stimulation modeling. This is the top row is the hydrofracts without natural fractures. There's a growth of 2 or 3 fractures per stage. It's predominantly upward growth. You can see this is the hydraulic aperture and the plot over here. This, you can see the stress shadowing effects. So stacking wells vertically, of course, makes most use of the hydraulic stimulation. So hydrofracts with natural fractures, a much more complex path due to the natural fractures. For most stages, there's less upward growth of the discrete hydrofracts due to the natural fracture intersections. And in some stages, natural fracture stimulation reaches a further distance because of these subvertical natural fractures that are growing into the existing stimulated fractures. So why zonal isolation? So it was really clear from the get-go. This is one of the early plots that we had from this phase, looking at this is the water rate along the well, the lateral, and you can see that specific perfs are taking most of the fluid. So operationally, we need to implement the flow conformance, in the model, it was pretty straightforward. We could shut in the perfs where the flow rate exceeds a certain amount so that we can equalize the flow along the wellbore. And this kind of flow conformance should be able to be handled by inflow control devices, ICDs, in the completion. And what's interesting is that this is a paper by Tom Doe and colleagues in 2014. It was using an analytical solution by Grengarten and found very similar kinds of declines did analyses from uniform spacing all the way to and uniform aperture to variable spacing to log normal to very variable aperture. And again, found they ran it for like 100 years, but it was about the same, 20% decline over 30 years. So what you're seeing here is this less distributed flow, lower residence time, it's higher thermal decline, less heat production, and earlier thermal breakthrough. So here are the key results from the phase 3 modeling. This is now looking at simulation with increasing well separation. And this is hydraulic fracture propagation into a natural fractured reservoir with and without zonal isolation. The different separation here is the distance of the producer above the injector. For each of these, 250 meters above the was the best. And you can see that in about 10 years, you had 8% decline. In about 30 years, is 25% decline. But with zonal isolation, it didn't make much difference. So it was about 7% and the same decline over 30 years. These plots that you'll see here are temperature, and you're seeing that in this particular case, it's 150 meter separation of the well, 250 meter separation. So you can see that you're getting, the breakthrough isn't as rapid, when you have that particular separation, which is good. So this is the simulation with increasing well separation. This again is hydrofracks without natural fractures, with and without zonal isolation. And in this case, you have a 20% decline in about 10 years and 55% in about 30 years with no zonal isolation. If you apply zonal isolation, you half that, and it's like 9% in 10 years. And you can see the more uniformity of the perfs and the flow across to the producer. So another plot here. This is really a summary of what I showed previously. The hydrofracks with natural fractures, there isn't that much difference in decline, but it does make a big difference for the hydrofracks without natural fractures, just the EGS by itself. This is an interesting plot here. It's a temperature profile across the producer and with and without zonal isolation. You can see that the lateral, the zonal isolation allows the temperature to reach a much higher value than without it. And in the case where you have natural fractures, it doesn't make much difference. It reaches a high temperature. So then the last part that I want to talk about is the economic analyses. We look at the surface plant conceptual design, data requirements for the basis of design, drilling engineering design with risk analysis, all of these costs, the well design and time and cost estimates. We looked at both DFN, EGS, and AGS for these sites to help clients understand what the best the best use of the site might be, and the economic assessment for a levelized cost of electricity and a cost breakdown. So for each of these development cases, the concept is of a doublet producer injector, except for this closed loop one well case, of course, and an organic Rankine cycle plant that converts the thermal heat to electricity. And this is a comparison of the relative LCOEs for phase 2 and phase 3. So you can understand how we were doing the down selecting. Very clearly here, AGS is far more costly than either EGS or just having natural fractures themselves. And the reason of the down selecting. Into phase 3, what you're seeing here, this trend of more cost if you do not have zonal isolation, and then this is the trend with getting that sort of Goldilocks, well separation that you need to have. Then the assessments, the economic assessments are based on the various economic and commercial assumptions for each well type. E&A de-risking costs, upfront costs over 2 years, power plant and other capex, operation and maintenance cost over 25 years. I mean, it's every detail, labor costs, water operation and maintenance, pumping. But note really that repurposing, for the AGS case, for example, repurposing existing oil and gas wells significantly reduce the capex. So this cost split here is these are interesting plots because you can see that, as John mentioned, that this is the well costs are the biggest cost, and if you can re-enter pre-existing wells, for example, and also if you're in an area as we were in South Texas where you have you have some knowledge of the, you may have ENA wells, and so you don't need to have this upfront cost of, of a perfectly, without any wells in the area, so that you may have some data to focus on. All right, so just in summary, so I guess all I wanted to say is that we've shown the potential for EGS locating sites in South Texas by drilling to about 5 kilometers, and that the relative LCOE is highly dependent on the subsurface conditions and really the starting conditions. So, in other words, if you have pre-existing well data or not, production wells must be positioned above the stimulate injected to exploit vertical growth of hydraulic fractures into regions of lower stress. That's very clear. Pre-existing natural fracture networks seem to enhance thermal output. Well separation has a significant impact on thermal output with respect to hydrofrac length, and zonal isolation flow conformance significantly improves the thermal output for the hydrofrac cases only. In fact, we would say it's a requirement. So I'll stop there.
Thank you very much, Colleen. That was excellent. Please put your questions for Colleen in the Q&A function. And next, I would like to introduce Kareem El-Sadi. Kareem is drilling engineer manager at Fervo. Before joining Fervo in 2023, Kareem amassed 10 years of oil and gas drilling and well engineering experience, primarily with Shell. And he holds a master's degree in mechanical engineering from UT Austin, as well as a master's degree in computer science from Rice University. So Kareem, thank you so much for being here, and the floor is yours.
All right, thank you. Yeah, hi everybody. Pleased to be here with you today. Like Anina said, I'm Kareem El-Sadi, drilling engineering manager at Fervo Energy. And today we'll be talking about modernizing geothermal field operations using some of the lessons that we've learned from our execution at Fervo. So, all right. So before we get started, wanted to do a little bit of a regrounding on our mission at Fervo as it relates to enhanced geothermal systems or EGS systems. We'll talk about how today's EGS systems differ from traditional geothermal that we may be familiar with, and why those differences breed opportunity as it relates to operational execution and development. We'll go through a short case study from our ongoing development at Cape Station in Utah and talk about how these differences manifest in practice using some real-world examples, and then we'll wrap up with a distillation of some of the key learnings that I'd say anchor how we execute and frame the lens through which we view and measure success. So starting off with our mission, fundamentally, it's very well established that the Earth harbors a lot of heat, and this heat has been the object of our collective great interest and attention for many years because of the sheer immense amount of energy stored beneath our feet. So while some areas are hotter than others, today's commercially accessible heat represents a power potential that we could only dream of before we had the modern technology evolve to where it's at today, and so enter enhanced geothermal systems. With these EGS systems, such as the one shown, which is the Fervo design, we're virtually geologically unconstrained, and we're, in a sense, in a pure pursuit of temperature. So we're targeting hot, dry rock through the installation of horizontal wellbores, connecting them via hydraulic stimulation, as opposed to targeting geologically constrained natural fractures that in formations that are highly localized. So with this, we're able to transform the energy landscape. And then when you superimpose a commercial reality on top of the technical opportunity, what we find is that today there's enough geothermal energy within a subsurface depth of 5 kilometers to fully satisfy US electrical demand. And if we were to go deeper to a depth of 7 kilometers, there's an electricity generating potential that can meet the US electric demand 5 times over. So quite a bit of opportunity. And that brings us to our mission. We know that there's a tremendous amount of potential to access clean and reliable and cost-effective, scalable geothermal energy. So our mission is thus to leverage innovation in geoscience to accelerate the clean energy transition by providing cost-effective, reliable geothermal energy. Okay, so that's the mission. And remember, we're here to talk about how we've modernized geothermal field operations at Fervo. So why would I want to start talking about traditional geothermal resources first? Aside from the commercial and energy potential limitations of traditional geothermal resources, there's a key attribute of those traditional geothermal fields that are developed that is, I think, sometimes underappreciated when we think about economic execution and large-scale commercial development. We established previously that they're geologically constrained. We know that with the geologic constraints, finding a viable geothermal resource is often an exercise that's steeped in some uncertainty and takes iterative trial. And when we combine somewhat limited deployment opportunities and higher subsurface uncertainty with variable power generation potential, what we end up with is, in some cases, a lot of start-stop operations. And so if we think of the plan, do, check, act cycle of optimization, where our goal is to learn from a large repetition count, we find that with traditional geothermal resources, there just isn't enough of a flywheel potential to make it all the way around the circle. And you have fewer opportunities for iterative improvement and systematic cost reduction, because the inherent intermittency is disruptive and antithetical to continuous improvement. So with the EGS opportunity, by contrast, you've got a subsurface target selection, which is largely driven by temperature, which is both abundant, like we talked about earlier, and very well understood. The reservoir performance is predictable and scalable because, in effect, it's the product of an engineered design as opposed to naturally occurring variability. So we're in control of the reservoir design. And when we combine the unconstrained nature of the opportunity with the predictable nature of power generation, what you find is now you have the right conditions for continuous operations in the field to develop these resources at scale. And so then iterative improvement, the flywheel starts to spin to our heart's content, really. And this is best visible from the days versus depth performance charts. So shown this one in the past, here with these days versus depth, we're contrasting offset geothermal wells that were drilled in Nevada. And then we've got our first couple of horizontal wells that Fervo drilled as part of Project Red, followed by the horizontal development wells at Cape Station in Utah, which are shown kind of to the left side of the graph. So immediately evident is the rapid improvement in drilling performance, right? So there's a key enabler to unlocking EGS commercial viability is the drilling time. And we've seen a lot of success there. But the more noteworthy point, and the one that I'm actually trying to emphasize on the slide, is if you look at how tightly bunched the lines on the left are, we're only able to drive this type of improvement because of repeat, continuous, iterative, and learning field operation. So this type of an operation is one where we're in a constant pursuit of building on the last success, systematically removing limiters and pushing the edge of the proverbial EGS envelope. So we can look at some examples of this learning flywheel in practice from Project Cape. With continuous operations, we're well positioned to rapidly iterate on bit designs and learnings, right? John talked about it earlier. We've graduated from the age of roller cone bits for hard rock. We've enabled the use of PDC bits to unlock these basement formations, and now as we drill more, we understand the contribution, the significance of cutter development, and how that plays a key role in allowing us to unlock drill rates that were deemed not attainable for many decades. With continuous operations, we're able to invest in modernizing the rig fleet using the latest in rig technology and automation. We electrify the rig for environmental efficiencies, and we're able to generate or deliver greater amounts of horsepower to the drilling operation. Again, because of the rep count, we're able to take a systematic, controlled, scientific approach to wellbore optimization, where we're trialing things in a disciplined manner with a very clear goal of drawing conclusive results, only because we've got the benefit of repeat and continuous operations to build on those learnings. We lean very heavily into surface and downhole data acquisition to develop these highly sophisticated models of the thermal and mechanical interactions in the subsurface, and that allows us to better plan our well and power plant designs. But then we're also able to validate the performance and benchmark our results periodically to marry that immense computing and modeling potential with grounded empirical data. And so thus we're able to elevate the quality and pace at which we can drive improvement. And yeah, we can invest in fit for purpose equipment. It allows us to go deeper and hotter and still maintain a safe environment and drive consistent, repeatable execution. So when you think of the flywheel in action, we could see that the attributes of a quote unquote modern geothermal field operation are predicated on having that ability to make investments that'll elevate the standard at which we execute and afford us the opportunity to learn repetition after repetition and unlock the data gathering potential that takes a conceptual design to a high precision exercise in field development. Okay, so while I think it's helpful for us to review that flywheel in action like we did, I did want to take some time and talk about some of the other practical takeaways that I've personally gleaned from these last couple of years being involved in the EGS journey at Fervo. I've noted a few points. These are more reflective in a sense, and it's less about what is enabled by continuous operations and more about how we actually go about enabling it in practice. Okay, so number one, there is no substitute for doing. Rapid iteration is what drives the learning curve. So as you could tell, this isn't a lab project. We're not doing this work on a test well somewhere or simulating results on a computer. We've drilled over 20 horizontals and stimulated multiple wells. And so these learnings that we've gathered over time are hard to come by without actually putting steel in the ground and making it happen. Second one, gather data and trust the data. It's one thing to go and do a bunch of things and, conduct operations, but if we're aimless in how we approach it, there's the risk that we miss the forest for the trees. And in a sense, what happens, we artificially downgrade our ability to learn. So every decision and every action, every operation needs to do one of two things. It needs to either feed the data gathering process or be informed by reliably gathered data. How we actually go about this is probably its own conversation topic and very involved, but very critical that we trust the data that we're gathering. This third point here, cross-functional integration makes the puzzle pieces fit. So EGS systems, it's one big connected system. In a sense, it's a dance of sorts, right? If every individual or every function or discipline is optimizing for their own KPIs, the system breaks down. We know inherently that each part of the system touches the next part. So the wells we drill are the wells that we complete. The wells we complete are the wells that we produce. The wells that we produce feed the well pad facilities, and it's all interconnected. And so decisions can't be taken in isolation, and decisions need to be made cognizant of the ripple effects that they have on the totality of the system. And I think that's one area that's been a boon for us, is having a very strong cross-functional integration to make the puzzle pieces fit. Okay. Limiter redesign is the lens through which improvement opportunities can be identified. You may have heard of the term limiter redesign. I think this was coined by Fred Dupree several years ago. It's now embraced really beyond the world of drilling. It's both kind of technical, but also I think of it as kind of a cultural term. And in a sense, what happens is we expect improvement by virtue of our process. So when we think about performance improvement, the view is that at any given moment in time, there can only be one thing that's limiting our performance from being elevated to the next level, whatever it is we're measuring, whether it's rate of penetration or bit run length or total power produced or so on. There's one limiter, and our goal and the focus of our attention is to identify that limiter and put our heads together to work it out of the system, and then move on to the next one and kind of continue to repeat that process. This one is a little bit of a softer one, but Kant is a self-imposed limiter. All of the biggest breakthroughs that we've seen at Fervo, drilling these horizontal wells in hard rock granite, running high temperature fiber in abrasive formations, high build rate control, all of these came from ignoring traditional boundaries. And I think the industry is doing this together, where we're slowly identifying these previous can'ts and thinking about what can we do to actually make it happen. I think the big problem with this word is it really kills the spirit of innovation. It stifles creativity, the creativity that we need to think about how we can actually be enablers for problem solving rather than buckling to the pressure of perception. So it's, like I said, a little bit of a softer one, but one that I think we can't stress enough. That word needs to be removed from our geothermal vernacular. Okay, the sixth one, early agility is the key to long-term stability. When we're talking about success at scale, it doesn't mean having perfect plans up front. It means having good plans and flexible ones. So we're talking about gathering data and trusting the data a few minutes ago. Trusting the data sometimes means that our initial hypotheses were proven otherwise, and it's in our best interest to make a pivot. And if we dig our heels in the ground and become rigid, then the opportunities for improvement and further learning will pass us by, and then stagnation becomes a real risk. So one of the things we try to maintain is the ability to pivot on, once we've received data that tells us that we should. And my last point here, operations without operational discipline is aimless and unrewarding. This one kind of ties back into that gather the data and trust the data comment, but discipline isn't just for process's sake. It's how we move, or we're able to move fast without breaking things. And so just doing a lot of work doesn't necessarily mean we're getting better. Every decision and every step forward needs to be very deliberate, and discipline has been the key to success in the evolution of EGS from our perspective. So with the tremendous opportunity we've had to maintain continuous operations, I'd say it's been the discipline that's allowed us to leverage the best of these opportunities and really see this endeavor through to its full potential. Yeah, like I said, wanted to leave it with a few of those softer type learnings because while they're mostly non-technical in nature, in my mind, they're the philosophic backbone of who we are and what we do at Fervo. I believe it's these points that are going to enable us to continue unlocking the next frontiers of EGS long into the future. And appreciate everyone for taking this time to indulge me, and I'll hand it back over for the Q&A portion and closeout.
Thank you, Kareem, and thanks for sharing those learnings and best practices. I think they're inspirational and something we can all take something from regardless of what our role is. So really appreciate you sharing those. All right, we have a few minutes for questions. So as a reminder, please add those to the Q&A functionality in the Zoom. We'll get started with one that'll be pretty quick for you, Kareem. On the Cape drilling slide that was presented, are the days represented on bottom days or total to completion?
Those are total spud to TD.
Okay, great. All right, so I'm curious, I'll keep it with you for a moment, Kareem. On the topic of limiter redesign, in your last slide, is there an example you can share of a limiter that you or Fervo has identified previously in their work, and how was that solved?
Yeah, there's many examples. Like I said, it's the focus of much of our attention is identifying what is the limiter. I'd say one of the more interesting ones is non-technical in nature, and it's a perceived limiter, where our offset experience would have suggested that running bits to a certain amount of weight on bit is problematic because we start to exceed structural integrity and we expect catastrophic failure of bits and so on. And expect dysfunction in tools. And what we found is a lot of the reasons we, would have hesitated to push the boundaries earlier on were not necessarily founded in the true physics. It was more offset experience, empirical based. This is what we've seen and done for many years and are hesitant to push the envelope. That was a kind of a mental limiter that we had to overcome and just really trust the data and see, run it until it breaks, and if it breaks, understand why. We implement the limiter redesign process on bits and cutters all the time. Every bit run comes out of whole, and we're looking at where did we start to see the initiation of wear, what caused that initiation, looking back at our run and our parameters, and working with the with our service providers and partners to understand what do we need to do to increase the resilience and the durability of the bit or the performance. So that's an example of a more technical limiter redesign exercise.
That's great, thank you. And I don't want to put you on the spot here, so if you can't share it, then go ahead and skip. But is there anything you can share in terms of a limiter that you've identified that you guys are working on currently, or something you see down the road that will continue to drive innovation and improvement?
Yeah, I would say obviously we're talking about geothermal operations. Temperature at some stage becomes a limiter, and tools and technology and the evolution of downhole technology to be able to unlock that next frontier, I think is recognized as one of the today limiters that I think in the tomorrow world will have overcome through innovation and ingenuity. So for sure, I think when you think about high temperature service for electronics, the industry's recognized that that there's a challenge with tool life, and that's the subject of a lot of interesting R&D and tool development.
Absolutely. It's a fascinating space to watch that will benefit all aspects of the geothermal industry with that innovation. Colleen, I'll hop over to you. I'm curious about your modeling with hydraulic fractures and natural fractures, how that interplay with zonal isolation and well spacing relates to thermal decline. I'm curious if you could expound a little bit on how you see the influence on geomechanics in the fine tuning of that. How, said another way, how well do those findings that you shared hold true for all geology types? Or is it very, geology, rock mechanics specific to your area?
Well, the fractures are going to propagate, in the direction of SH max. I mean, we all know that. But the unknown is the geometry of any other imperfection, if you have some background natural fractures, you don't know what their orientation is a priori often, and you have to stimulate to find them basically with microseismic, So that's one limiting issue, and it's the data needs to be acquired to know what the geology is, and that's why we go to all the for each of these down selected sites. Again, we're not we're trying to help our clients figure out where to invest, and so for each of the sites we've built a full geomechanical model. It's a requirement. We have to know the pressures. I mean, we know that. So I guess your question is it site specific? Yes, very. So, and therein lies the problem. There's no cookie cutter out there. There's no way to say, oh, this is granite. So there, and so I mean, there's tombstone granite, it's tombstone, with no natural fractures, and there's some that are completely, fractured. So so that's just a short answer to your question that could be very long.
I appreciate it. Thanks, Colleen. Well, we just have a couple minutes left, so I want to give you both an opportunity to answer this. And this is maybe a little bit of a vague question, so take it in whatever direction you would like. What would you say to the skeptics out there of EGS? There's a lot of talk about concern around rates of thermal decline, among other things. But what's your take on that? How would you respond to someone who's very skeptical of the long-term viability of EGS as an energy source going forward?
Yeah, I can go ahead and get kicked off. I would say the skepticism is not new. It goes back to pre the first EGS wells, and it continues. I think one of the things that's changed is we've gathered a lot of data. We have real wells in the ground with real data, fiber optic data, well production data, fracture data, microseismic, so on and so forth, that help inform the future. And so while the skepticism is natural, because I think anything relatively new and novel and kind of change instigating can come with a lot of questions. I think our goal and our mission is to continue to answer those questions and continue with the exercise of de-risking as we've done, continue to share and build on build on what we've done so far. But yeah, Colleen, not sure if you got anything to add.
I just, I agree. I mean, for example, you mentioned the decline is, what is everybody's saying is they're so skeptical, but this is, you've got to, as Kareem said, this is a can't, we have to get above, we have to get over that. And we're now finding it. And so we're trying to figure out, like, zonal isolation is one solution, possibly, but industry has to be able to, do we have, the right equipment to be able to get that flow conformance at those temperatures? This is the challenge. And yeah, there's skepticism, but there's just the opportunity is vast. There's a lot of heat down there and there's a lot of need for electricity. So that's only going to increase. So I'm not at all put off by skepticism. They always, what's the old adage? They always say at first that you're just crazy, and then at last they finally say it was blindingly obvious that we were doing it right, So, but yeah, so skepticism is motivating.
That is very inspiring and a great place to wrap it up on. And it's really great work, like the people like you and your colleagues at Baker Hughes, Utah Forge, and Fervo that are answering those questions and doing the important technical work that will get us to the sustainable energy future that EGS can provide. So thank you all so much for joining us, and we hope to see you in a couple of weeks at our next Full Steam Ahead webinar. Thank you. Take care.
The opportunity. Bye now.
Thanks.